Have you ever held a piece of metal, like gallium, and actually felt it melt right in your hand? It's pretty remarkable, isn't it?
It really is. Quite startling the first time.
Yeah. And then you think about something like table salt, sodium chloride. You'd need temperatures, what, almost 27 times higher just to get that to melt?
That's right. An enormous difference.
So what makes these seemingly simple substances behave so incredibly differently?
Welcome to the deep dive, where we try to extract the most important insights from, well, often complex topics. Today, we're plunging into the fundamental forces holding matter together, chemical bonds. Our mission really is to explore the three main models, ionic, covalent, and metallic bonding, and understand how these models are, the key to explaining the properties we see all around us. We'll be drawing insights from Silverberg and Amatese's chemistry, the molecular nature of matter and change. We want to guide you through the big ideas, the laws, the examples, turning dense concepts into something clear and engaging.
And it really starts with a foundational question in chemistry.
Yeah.
Why do atoms even bother bonding at all? Right. What's the driving force?
What's fascinating here is that bonding isn't just a random thing. It's driven by a universal principle. Atoms bond to achieve a lower potential energy state, a more stable arrangement. You can almost think of it as a kind of cosmic settling down. Once they're bonded, they found their most comfortable, stable spot, and they'll resist being pulled apart.
Okay, so stability is the goal. We've got these dramatically different substances, salt and gallium, and this fundamental drive for stability. But how do atoms actually do it? What are the mechanisms?
Well, if you look at the periodic table, you see this clear gradient, right? From metals on the left over to nonmetals on the right.
Mm-hmm.
And this spectrum basically dictates three main ways atoms combine. First, when a metal meets a nonmetal, we typically see electron transfer. This forms ionic bonds. Think of those really reactive metals from groups 1A and 2A. They're eager to lose electrons. And they meet nonmetals from groups 6A and 7A, which are just as eager to gain them. So the metal transfers one or more electrons to the nonmetal. This creates oppositely charged ions, positive cations and negative anions, which then attract each other very strongly.
Into that rigid 3D structure, the ionic solid we mentioned, like salt.
Exactly, that's ionic bonding. Second, if you have a nonmetal with another nonmetal, now you get electron sharing. This is covalent bonding. In this case, neither atom really wants to give up electrons easily, so instead they share electrons to achieve stability.
Ah, like a compromise.
Precisely. These shared pairs create a specific localized bond between those two atoms, often forming distinct molecules, things like water, H2O, or carbon dioxide, CO2. And finally, there's metal with metal. This involves something different, electron pooling. We call it metallic bonding.
Electron pooling, how does that work?
Metals are, well, they're special. They have outer electrons that are held pretty loosely. They aren't individually shared between just two atoms, and they aren't completely transferred. Instead, lots of metal atoms pool their valence electrons together into this kind of sea of electrons. This sea can move freely throughout the entire piece of metal.
Wow. Okay.
And it holds together what we call the positively charged atomic cores, basically, the nucleus and the inner electrons of each metal atom, all sitting within this mobile electron sea.
That's a really different picture. So, okay, three main ways: transfer, sharing, pooling. Now, how do we start predicting which atoms will do what? Is there some kind of, I don't know, target they're aiming for?
Absolutely. And it's actually elegantly simple most of the time. It's the octet rule. But first, just to help visualize this, we use something called Lewis electron dot symbols.
Ah, yes, the dots.
Right. They're just a simple shorthand. You write the element's symbol, and then you put dots around it, representing its valence electrons, those outer electrons involved in bonding. The number of dots tells you immediately how many electrons an atom might want to gain, lose, or share.
Right. And this leads straight to the octet rule, which you said is kind of the chemical holy grail for most atoms.
Pretty much. It states that when atoms bond, they tend to lose, gain, or share electrons to achieve a stable outer shell containing 8 electrons, just like the noble gases, which are very unreactive because they already have that stable configuration.
So 8 is the magic number, though hydrogen and lithium are exceptions, right? They're happy with just 2.
Correct. They aim for a duet, like helium. But for most others in the main groups, 8 is the goal. So these Lewis symbols become really powerful predictive tools.
Okay, give me an example, like magnesium.
Good one. Magnesium is in group 2A, so it has 2 valence electrons. Its Lewis symbol shows 2 dots. This immediately suggests it's likely to lose those 2 electrons to become a stable Mg2 plus ion, achieving the electron configuration of neon.
And fluorine. over on the other side.
Fluorine, group 7A, has 7 valence electrons. Its Lewis symbol shows 7 dots, meaning one electron is unpaired.
Ah, so it just needs one more to get to 8.
Exactly. That symbol visually signals its strong desire to gain one electron and become the F ion, completing its octet. It directly links the symbol to its bonding behavior. And that drive for the octet perfectly explains the electron transfer and ionic bonding we talked about. Sodium, Na, loses one electron to become Na plus a rho. Oxygen O needs 2, so it gains 2 to become O2.
And to make a neutral compound, you need the charges to balance. So 2 sodiums for every 1 oxygen gives you Na2NeO. Makes sense.
Precisely.
But hang on, you mentioned earlier that forming gaseous ions actually takes energy, it absorbs energy. If that's the case, why are ionic compounds like salt so incredibly stable? Where's the big energy payoff?
That is the crucial question. And the answer lies in something called lattice energy.
A lattice energy. Okay.
This is the enormous amount of energy that gets released when those individual gaseous ions, Na plus and Cl for salt, for example, come together from the gas phase to form the highly ordered crystalline solid.
So it's not forming the ions, it's building the crystal. That's the key.
Exactly. This incredibly strong electrostatic attraction between countless positive and negative ions, all locked into that rigid 3D lattice, is the real energetic powerhouse. The energy released here far, far outweighs the energy needed to create the ion in the first place.
Yeah.
That huge release of energy makes the overall process very favorable, very exothermic, and results in those really stable ionic solids.
Wow. So it's the act of constructing that crystal lattice that provides this immense stability, almost like it overcomes the initial cost of making the ions. That's really fascinating. And how do chemists actually figure out this lattice energy? It sounds like something you can't just measure directly.
Well, not easily directly, no. We use a clever thermodynamic tool called the Born-Haber cycle.
Okay, Born-Haber cycle. Sounds complex.
Don't worry, we won't do the math. But picture it like this. The Born-Haber cycle is like a meticulous chemical accountant. It breaks down the whole process of forming an ionic solid into a series of hypothetical steps, each with a known energy change.
Steps like what?
Like turning the solid metal into gas atoms, breaking the non-metal molecules into gas atoms, ionizing the metal atoms, that's ionization energy, adding electrons to the non-metal atoms, electron affinity.
Okay, so all the preliminary steps.
Right. And then the final step is letting those gaseous ions snap together into the crystal lattice. That's the lattice energy step. By knowing the energy for all the other steps and the overall energy change for forming the solid from its elements, which we can measure, we can calculate that missing piece, the lattice energy.
It's like solving for X in an energy equation.
Exactly. And what it consistently shows is that the lattice energy term is huge, usually the largest energy component, and it's negative energy released. It demonstrates the power of that electrostatic attraction in the solid state.
That's a neat way to quantify it. And zooming out again, what influences how big this lattice energy is? Are there trends?
Absolutely. It's directly influenced by two main things: the size of the ions and the magnitude of their charges. And this is beautifully described by Coulomb's law.
Coulomb's law reminds me of physics class. Opposite charges attract, like charges repel.
That's the one. And it also says the force is stronger for larger charges and smaller distances between them. So first, the effect of ionic size. Smaller ions mean their centers of charge are closer together. Closer distance means stronger attraction, according to Coulomb's law. Stronger attraction means a higher lattice energy. More energy is released when they form the lattice.
So as you go down a group in the periodic table, ions get bigger.
Right, they get larger, so the distance between ion centers increases, the attraction weakens, and the lattice energy decreases. Think of lithium fluoride, lift tiny ions, very high lattice energy. Compare that to, say, rubidium iodide, RBI, much larger ions, significantly lower lattice energy.
Okay, size matters. What about charge?
Charge has an even bigger effect, the effect of ionic charge. Higher charges lead to much, much stronger attractions and significantly higher lattice energy. Compare life, again, that's a +1 charge on lithium and a -1 on fluoride with magnesium oxide, MgO. Magnesium is +2, oxygen is -2.
So double the charge on both ions.
Exactly. Even though the ions might be similarly sized, MgO's lattice energy is nearly 4 times higher than life's.
4 times. Why so much?
Because Coulomb's law involves the product of the charges. So for leaf, it's like 1 times 1. For MgO, it's 2 times 2. That difference from 1 to 4 makes a huge impact on the electrostatic force and thus the lattice energy.
Got it. Size and especially charge. So what does this tell us about the actual observable properties of these ionic compounds? How does it explain things like salt being hard but brittle?
Their properties make perfect sense now. They are typically hard because those ions are held in very specific, fixed positions by strong electrostatic forces. It takes a lot of energy to disrupt that ordered structure.
But brittle, why do they shatter?
Because if you apply enough force, say you hit a salt crystal, you can shift the layers of ions just slightly. If you shift them just right, you can bring ions with the same charge next to each other.
Ah, positive next to positive, negative next to negative.
Right, and then you get massive repulsion between those, charges, which causes the crystal to crack and shatter suddenly along a clean plane. It doesn't bend, it breaks.
That makes sense. And those incredibly high melting and boiling points we started with for salt.
Directly related to the high lattice energy, you need to pump in a huge amount of thermal energy to overcome those strong electrostatic attractions and allow the ions to move freely past each other, which is what happens when it melts or boils.
Okay. And electrical conductivity.
Again, it fits the model. In the solid state, the ions are locked in place in the lattice. They can't move, so solid ionic compounds don't conduct electricity.
But if you melt them.
Or dissolve them in water, yes. Then the ions are freed up. They become mobile charge carriers. So molten ionic compounds, or aqueous solutions of them, do conduct electricity very well. It's a key characteristic.
Right. That makes perfect sense. Okay, so that's ionic bonding. What about the other major type, covalent bonding? This accounts for most compounds, right?
The vast majority, yes.
Hmm.
Things like plastics, organic molecules, water.
Mm-hmm.
Here, as we said, nonmetal atoms share electrons instead of transferring them.
Hmm.
Picture two hydrogen atoms approaching each other. When they're far apart, they basically ignore each other.
Okay.
As they get closer, the nucleus of each atom starts to attract the electron of the other atom. At the same time, you have repulsions, nucleus, and electron. There's a sweet spot, a specific distance, where the attractions, nucleus to the shared electrons, are maximized and the repulsions are minimized.
Hmm.
This lowers the overall potential energy of the system compared to the separate atoms.
And that sweet spot distance is the bond length.
Exactly. That stable distance is the bond length. And the amount of energy released when the bond forms from the separate atoms, or the energy needed to break it, is the bond energy. The key insight is that in a covalent bond, the shared electron density becomes concentrated between the two positively charged nuclei, acting like an electrostatic glue pulling them together.
So the electrons are now owned by both atoms, in a way?
That's how they count them for the octet rule, yes. Those shared electrons are called bonding pairs, and any valence electrons on an atom that are not involved in bonding just stay as lone pairs. And what's really remarkable is that every covalent bond has three properties that are fundamentally linked: bond order, bond energy, and bond length.
Okay, tell me about those. Bond order sounds simple.
It is. Bond order is just the number of shared electron pairs between two atoms. A single bond, like an HH or CC, has one shared pair, so its bond order is 1. A double bond, like OOO in oxygen gas or CC in ethylene, shares 2 pairs, bond order 2. And a triple bond, like N in nitrogen gas, shares 3 pairs, bond order 3.
Simple enough bond energy.
Bond energy, sometimes called bond strength, is the energy required to break 1 mole of that specific bond in the gas phase. It's always a positive value because you have to put energy in to break a bond. Stronger bonds have higher bond energies.
And bond length.
Bond length is simply the average distance between the nuclei of the two bonded atoms.
Okay, so order, energy, length, you said they're linked. How?
It's a really important relationship. Think about it. A higher bond order means more electron pairs are being shared between the two nuclei.
Right, more glue.
More glue, exactly.
Yeah.
More electrons pulling the nuclei together leads to a stronger attraction. This stronger attraction pulls the nuclei closer together, resulting in a shorter bond length. And because the attraction is stronger, it takes more energy to pull them apart, meaning a higher bond energy.
Ah, so higher bond order means shorter length and higher energy, stronger bond.
Precisely. For example, a typical carbon-carbon single bond, CC order 1, is longer and weaker than a carbon-carbon double bond, CC order 2, which in turn is longer and weaker than a carbon-carbon triple bond, CC order 3. This scaling relationship is fundamental.
That's a powerful connection, but it brings up a puzzle. If these individual covalent bonds, especially double and triple bonds, are so strong, why are so many covalent compounds like methane or wax or even water, gases, liquids, or low-melting solids? It seems like they should be tougher.
That is an excellent question, and it highlights a really critical distinction in the covalent world. The answer lies in understanding two different kinds of forces. There are the strong intermolecular forces, those covalent bonds within a single molecule holding the atoms together.
Okay, intro within.
Right. But then there are much, much weaker intermolecular forces. These are the attractions between separate individual molecules.
Interpret me.
So when you boil water, for instance, you're not breaking the strong OH covalent bonds inside the water molecules. That would take a huge amount of energy.
Right, you'd be decomposing water into hydrogen and oxygen gas.
Exactly. Instead, you're just overcoming the relatively weak attractions between one water molecule and its neighbors. These intermolecular forces are what hold the water molecules together in the liquid state. Once you add enough energy, at 100 degrees C, you overcome those weak forces, and the molecules can fly off separately as gas.
Ah, okay. So the low melting and boiling points of most molecular covalent substances reflect the weakness of the forces between molecules, not the strength of the bonds within them. That explains methane being a gas, water a liquid, wax a soft solid.
Precisely. That distinction is key.
Yeah.
However, there's an important class of covalent substances where this doesn't apply. Network covalent solids.
Network covalent, like diamond.
Diamond is the classic example. Quartz, silicon dioxide is another. In these materials, the covalent bonds don't just exist within discrete molecules. Instead, they extend throughout the entire crystal, forming a continuous network. Every atom is covalently bonded to its neighbors in a giant three-dimensional structure.
So there are no separate molecules to pull apart.
Correct. To melt something like diamond or quartz, you actually have to break those incredibly strong covalent bonds throughout the solid.
Which takes a massive amount of energy.
A massive amount. That's why diamond is the hardest known natural substance and has an extremely high melting point. You're fighting against those strong directional covalent bonds everywhere.
Got it. So molecular covalent compounds generally have low melting points due to weak intermolecular forces, while network covalent solids have very high melting points because you have to break strong intermolecular covalent bonds.
You've got it. And what about electrical conductivity for covalent compounds?
Well, if the electrons are locked into shared pairs, bonding pairs, or stuck on one atom, lone pairs, they aren't free to move around like in metals or molten ionic compounds, right?
Exactly right. So most covalent substances, whether molecular or network, are poor electrical conductors. They're
Sure.
insulators. The electrons are localized.
Okay. Now, how do chemists actually probe these bonds? You mentioned identifying them. What are the tools?
One incredibly powerful tool is infrared IR spectroscopy.
IR spec, okay.
The idea is that molecules aren't static. Their bonds are constantly vibrating, stretching back and forth, bending like tiny springs.
Vibrating bonds?
Yeah, and different types of bonds, like a CH bond versus an OH bond, or a CO double bond versus a CC single bond, vibrate at different characteristic frequencies. It depends on the masses of the atoms and the strength of the bond, that bond energy we talked about.
Okay, so each bond type has its own vibrational fingerprint.
That's a perfect way to put it. Now, IR spectroscopy works by shining infrared light, which covers a range of frequencies, onto a sample of the compound. If the frequency of the IR light exactly matches the natural vibrational frequency of a particular bond in the molecule absorbs energy from that light, causing that specific vibration to become more intense.
Ah, like resonance.
Very much like resonance. So by measuring which frequencies of IR light are absorbed by the sample, we get an IR spectrum. This spectrum is essentially a plot showing absorption versus frequency. And because different functional groups like OH, CO, CH, etc., absorb at very specific known frequencies, this spectrum acts like a unique fingerprint that tells chemists exactly what kinds of bonds, and therefore what functional groups, are present in the molecule. It's a primary way we identify unknown compounds or confirm the structure of synthesized ones.
That's really clever, using molecular vibrations to see inside the molecule. So we understand how bonds form, their strengths, their lengths, how to identify them. What happens when these bonds break and new ones form during a chemical reaction? We often talk about reactions releasing or absorbing heat, the enthalpy change. Where does that energy actually come from?
That's a fantastic question, and it ties everything together. It's not magic. That heat released or absorbed, the enthalpy of reaction, say ΔRxn, comes fundamentally from the difference in bond energies between the reactants and the products.
Difference in bond energies. How so?
Think of any chemical reaction as basically a two-step process, conceptually at least. First, you have to break all the existing chemical bonds in the reactant molecules.
And breaking bonds always requires energy input, right? Like you said with bond energy.
Always requires energy. It's an endothermic process. So step one costs energy. Then step two is the formation of all the new chemical bonds in the product molecules.
And forming bonds releases energy.
Yes, forming bonds is always an exothermic process. Energy is released as the atoms settle into a more stable, lower energy bonded state. So the overall enthalpy change for the reaction of HEGRXN is essentially the sum of the energy you spent breaking bonds, positive value, plus the energy you got back forming bonds, negative value.
Okay, so it's like an energy balance sheet, energy invested versus energy returned.
Exactly. We can even estimate this AHRXN using tabulated average bond energies. We look up the energy needed to break every bond in the reactants, sum those up. Then we look up the energy release when every bond in the products is formed, sum those up, making the negative. The net result is our estimated ATGRXN. And what does the sign tell us?
If HSRXN is negative, the reaction is exothermic. That means more energy was released when the stronger product bonds formed than was needed to break the weaker reactant bonds. The products are more stable, have lower potential energy than the reactants.
Like burning fuel?
Precisely. Combustion reactions are highly exothermic. Conversely, if HRGN is positive, the reaction is endothermic. More energy was absorbed to break the strong reactant bonds than was released when the weaker product bonds formed. The products are less stable, have higher potential energy than the reactants. You have to continuously supply energy to make it happen.
This directly connects to the energy we get from fuels and foods then.
Absolutely. When you burn gasoline, mostly hydrocarbons, or when your body metabolizes carbohydrates or fats, you're carrying out exothermic reactions. You're breaking relatively weaker bonds, like CC and CH bonds, in fuel or food molecules, and forming much stronger bonds in the products, primarily the OH bonds in water and the CO double bonds in carbon dioxide. And the large difference in energy between the weak bonds broken and the strong bonds formed is released as heat.
Exactly. That's the energy that powers your car or your body.
So this even explains why fats contain more calories per gram than carbohydrates, doesn't it? I always wondered about the chemistry behind that.
It does. It comes down to the types of bonds. Fats have a higher proportion of CC and CH bonds compared to carbohydrates, which have more CO and OH bonds.
Okay. And CC and CH bonds are generally weaker than CO and OH bonds.
Yes, significantly weaker than the CO and OH bonds formed in the products, CO2 and H2O. So when you metabolize fats, you're starting with molecules that have more of these relatively high-energy, weaker bonds. Breaking them costs less energy, and then you form the same very stable products, CO2 and H2O. This means the net energy release is greater for fats than for carbohydrates, gram for gram. It's all about the relative strengths of the bonds you break versus the bonds you make.
That's a fantastic connection between bond energies and everyday nutrition and energy. Okay, so we've covered the sort of pure cases. Ionic bonding with complete electron transfer and covalent bonding with electron sharing. But you implied reality is often messier. Most bonds aren't purely one or the other.
That's right. In the real world, there's a continuous spectrum between pure covalent bonding, equal sharing, and pure ionic bonding, complete transfer. Most bonds fall somewhere in between. We call these polar covalent bonds.
Polar covalent, so sharing but unequal sharing.
Exactly. And the concept that helps us understand and quantify this unequal sharing is electronegativity, often abbreviated EN.
Electronegativity, what is that exactly?
Electronegativity is a measure of the relative ability of a bonded atom to attract the shared electrons towards itself. Imagine those two atoms in a covalent bond playing tug-of-war with the shared electron pair. The atom with the higher electronegativity pulls the electrons more strongly.
Okay, a chemical tug-of-war. Who wins?
Well, on the most common scale, the Pauling scale, fluorine, is the champion. It's assigned the highest electronegativity value, 4.0. It's the best electron polar. At the other end, you have elements like cesium, Cs, or francium, Fr, in the lower left corner of the periodic table. They have very low electronegativity values, around 0.7 or 0.8. They're not good at attracting shared electrons. In fact, they tend to lose their own easily.
And are there trends for electronegativity on the periodic table?
Yes, clear trends. Electronegativity generally increases as you go from left to right across a period.
Why is that?
Because as you go across a period, the nuclear charge increases, pulling the electrons more strongly. But the electrons are being added to the same outer shell, so they don't get much further away or shielded. Smaller atoms with a stronger nuclear pull are better at attracting shared electrons. And electronegativity generally decreases as you go down a group.
Because the atoms get bigger.
Right. As you go down a group, the valence electrons are in shells that are progressively further from the nucleus and are shielded by more inner electron shells. So the nucleus has less pull on those distant shared electrons.
So top right, Excluding noble gases is high En, bottom left is low En. Makes sense. Now, how does this relate to bond polarity?
When two atoms with different electronegativities form a covalent bond, that tug of war is unequal. The shared electron pair spends more time closer to the more electronegative atom. This gives the more electronegative atom a slight buildup of negative charge. We call this a partial negative charge, denoted pred delta minus.
And the other atom?
The less electronegative atom is left slightly electron deficient, giving it a partial positive charge, plus delta plus. This separation of charge, a positive N and a negative N, is what makes the bond a polar covalent bond. It has a bond dipole. We often draw a special arrow, a polar arrow, along the bond pointing toward the more electronegative atom, the N, to show this electron shift.
And the difference in electronegativity between the two atoms tells us how polar the bond is.
Exactly. The electronegativity difference between the two bonded atoms is a direct measure of the bond's polarity. If AN is zero, like between two identical atoms, ClCl and Cl2 for example, the sharing is perfectly equal. That's a nonpolar covalent bond. If AN is small to moderate, say roughly 0.4 to 1.7, the bond is generally considered polar covalent. The larger the A, the more polar the bond, meaning the partial charges are larger. We say it has greater partial ionic character.
And if An is very large, like between a metal and a nonmetal?
If AN is very large, typically greater than 1.7 or 2.0, though there's no sharp cutoff, the pole is so unequal that the electron is essentially transferred, not shared. That's when we classify the bond as primarily ionic. Even in highly ionic bonds, though, there's usually still a tiny degree of electron sharing, so it's really a continuum.
So electronegativity difference provides the scale for this whole spectrum from perfectly equal sharing, nonpolar covalent, through unequal sharing, polar covalent, to almost complete transfer, ionic.
Precisely. It bridges the gap between our simple models and chemical reality.
Can you give an example showing this gradation, how properties change as the bond type shifts?
Yes, a classic example is looking at the chlorides of the period 3 elements, going across the periodic table from left to right. Start with sodium chloride, NaCl. Sodium's En is low, 0.9. Chlorine's is high, 3.0. The En is 2.1, very large.
Clearly ionic.
Clearly ionic. It's a white crystalline solid, high melting point, 801 degrees C. Conducts electricity when molten. Classic ionic behavior. Next, magnesium chloride, MgCl2. Magnesium's En is a bit higher, 1.2. En is now 1.8, still large, still considered ionic. Also a solid high melting point, 714 degrees C. Conducts when molten, but maybe slightly less ideally ionic than NaCl.
Okay, keep going across. Aluminum.
Aluminum chloride, LCl3. Aluminum's En is 1.5. Tn drops to 1.5. Now we're in the territory often considered polar covalent or perhaps ionic with significant covalent character. Its structure is different, more layered, and its melting point is much lower. It actually sublimes at 180 degrees C. It's a poor conductor even when molten. The properties are shifting.
Definitely changing. What about silicon?
Silicon tetrachloride, SeCl4. Silicon's En is 1.8. The N is now 1.2, clearly polar covalent. SeCl4 is a simple molecular compound consisting of discrete SeCl4 molecules. It's a liquid at room temperature, boils at only 58 degrees C, and doesn't conduct electricity at all.
Wow, big change.
Huge change. And it continues. Phosphorus trichloride, PCl3, sulfur dichloride, SEL2, crayon, keeps decreasing. These are also molecular liquids or gases with low boiling points, no conductivity. Finally, you get to chlorine itself, Cl2. Two chlorine atoms, En 3.0 each. En is 0.
Perfectly nonpolar covalent.
Perfectly nonpolar covalent. It's a gas at room temperature, consists of the discrete Cl2 molecules, no conductivity.
Yeah.
So that journey across period 3 chlorides beautifully illustrates the transition. As En decreases, the bonding shifts smoothly from ionic to polar covalent to nonpolar covalent, and the physical property, structure, melting point, conductivity change dramatically and predictably along with it.
That's a fantastic illustration of the concept. A chemical journey from electron swapping to equal sharing, mirrored in the substances themselves.
Okay, we've covered the electron swappers, ionic, and the electron sharers, covalent. But metals, they don't seem to fit either model neatly. How do they hold together, giving them properties like being shiny, bendy, and conductive?
Right. Metals require their own model. Metallic bonding, explained by the electron C model.
The electrons, we touched on this earlier. Can you elaborate?
Sure. The basic idea is that in a piece of metal, all the metal atoms contribute their valence electrons, those loosely held outer electrons, to a common pool. These electrons are no longer associated with any single atom. They become delocalized. They form a mobile sea of electrons that permeates the entire metallic crystal.
And what about the atoms themselves?
The atoms become positively charged ions, cations, consisting of the nucleus and the tightly held inner core electrons. These positive metal ions are arranged in a regular, orderly lattice structure, immersed within that flowing sea of negative electrons. So, positive ions sitting in a sea of mobile negative electrons. How does this explain metal properties?
It explains them remarkably well. Let's take their melting and boiling points. Metals typically have moderate to high melting points,
Why not always super high like ionic solids?
because when a metal melts, the ions gain enough energy to move around, but they are still strongly attracted to that electron sea. The overall attraction isn't completely broken just by melting, so it takes significant energy, but perhaps not as much as breaking down a rigid ionic lattice completely. However, metals generally have very high boiling points.
Ah, why the difference?
Because to boil a metal, you have to completely separate individual metal atoms from each other and from that shared electron sea. You have to vaporize them into independent gas atoms. That takes a huge amount of energy to overcome all those metallic bonds.
Like your gallium example melts in your hand but boils over 2400 degrees C.
Exactly. That huge liquid range is characteristic of many metals and reflects this difference between overcoming lattice rigidity, melting, and complete atom separation, boiling.
Mm.
Now think about their mechanical properties, malleability and ductility.
Right. Metals can be hammered into sheets, malleable, or drawn into wires, ductile. Ionic crystals just shatter. Why?
It's the electron sea.
Mm.
If you apply a force to a metal, you can push the layers of metal ions past each other. Because the electrons are mobile and surround the ions can slide without ever coming into direct contact with other positive ions and experiencing strong repulsions.
Ah, the electron sea acts like a flexible glue or lubricant, allowing the ions to rearrange without breaking the overall structure.
That's a great way to put it. Unlike ionic crystals, where a slight shift causes like charge repulsion and shattering, the metal just deforms. This allows for incredible shaping. Think about gold leaf. It can be hammered into sheets just a few hundred atoms thick. That's only possible because of this bonding model.
Amazing. And finally, the defining traits, electrical and thermal conductivity.
Again, it's all about those mobile delocalized electrons in the sea. Because they're not tied to any specific atom and are free to move throughout the metal lattice, they can easily flow in response to an applied voltage.
Carrying charge, that's an electric current.
Precisely.
Yeah.
And those same mobile electrons are also very efficient at transferring kinetic energy heat from one part of the metal to another. That's why metals conduct heat so well and feel cold to the touch. They rapidly conduct heat away from your hand.
So the electron sea model provides a really elegant explanation for this whole suite of unique metallic properties.
It really does. It captures the essence of metallic bonding beautifully.
Okay, let's try to wrap this up. We've covered a lot of ground in this deep dive into the molecular nature of matter and change. What are the key takeaways? We started by understanding the fundamental why of bonding. Atoms combine to achieve a lower potential energy, a more stable state. That's the driving force. Then we explored the three main models: ionic bonding, electron transfer between metals and nonmetals, driven by the huge energy release of forming a crystal lattice, lattice energy. This explains why they're hard, brittle solids with high melting points that conduct electricity only when molten or dissolved.
Right.
Then covalent bonding, electron sharing between nonmetals. We saw the relationship between bond order, bond energy, strength, and bond length, and the crucial difference between strong intramolecular bonds and weak intermolecular forces, explaining why most molecular substances have low melting points, while network covalent solids like diamond are incredibly tough.
And generally poor conductors.
Right. And third, metallic bonding, that unique electron sea model, with delocalized electrons holding positive metal ions together. This explains why metals are malleable, ductile, and excellent conductors of heat and electricity.
A good summary.
We also saw how electronegativity provides the bridge between pure covalent and pure ionic bonding, leading to polar covalent bonds with unequal sharing and partial charges, and how the electronegativity difference dictates where a bond falls on the spectrum, influencing the substance's properties, as shown by that period 3 chloride example.
Yeah, that continuum is key.
And finally, we connected bond energies directly to the heat released or absorbed in chemical reactions. Breaking bonds costs energy, forming bonds releases energy. The balance determines if a reaction is exothermic or endothermic, even explaining why fats pack more energy per gram than carbs.
It all ties back to the stability of those chemical bonds. You know, this understanding of chemical bonding, it really changes how you look at the world, doesn't it? It raises an interesting thought. As you look around right now at all the different materials, the plastic of your phone case, the metal legs of a chair, the glass in the window, maybe even the salt on your lunch, Can you start to see the invisible bonds holding them together? Can you begin to predict why the plastic is flexible, why the metal conducts heat, why the glass is transparent and brittle, based on whether electrons are being transferred, shared equally, shared unequally, or pooled in the sea? That's the real power of understanding these fundamental models.
That's a great point. It gives you a new lens through which to view the material world. We certainly hope this deep dive has given you a shortcut to being well informed on these core concepts and illuminated some of the molecular nature of matter and change. Thank you for joining us on this exploration. This has been the deep dive, and from the Last Minute Lecture team, thank you for listening.